So, good evening everyone. We are the group 9 and we are assigned to report the chapter 11, which is the simple linear regression and correlation. So, this is our assigned topic, the 11 to 1 empirical models, 11 to 2 simple linear regression, 11 to 3 properties of the least squares estimators, 11 to 4 hypothesis test in simple linear regression, which will be reported by um, Giancarlo Deloso, and then 11 to 4.1 use of t-test, 11.4.2 analysis of variance approach to test significance of regression, 11.5 confidence intervals, and 11.5.1 confidence intervals on the slope and intercept, and that will be discussed by Jonalyn Nugget. And then 11 to 5.2 confidence interval on the mean response, prediction of new observations, adequacy of the regression model, residual analysis, and that will be reported by Pearl Jason C. Alonso. And then 11 to 7.2 coefficient of determination or R squared, correlation, 11 to 8 correlation, 11 to 9 regression or transform variables, and then last is the 11 to 10 logistic regression, and that will be reported by me. I'm Bohos Jenvison, by the way. Thank you. And these will be our objectives for chapter 11. Number 1 is use simple linear regression for building empirical models to engineering and scientific data. 2 is to understand how the method of least squares is used to estimate the parameters in a linear regression model. 3. Analyze residuals to determine if the regression model is an adequate fit to the data or to see if any underlying assumptions are violated. 4. Test the statistical hypothesis and construct confidence intervals on the regression model parameters. 5. Use the regression model to make a prediction of a future observation and construct an appropriate prediction interval on the future observation. And then 6. Apply the correlation model. And lastly, use simple transformations to achieve a linear regression model. So this topic will be discussed by Mr. Giancarlo Diloso.
Good day, everyone. And my topic is about empirical models. So today we're going to discuss about empirical models and the following three topics. So empirical models. Many problems in engineering and science involve exploring the relationship between two or more variables. Regression analysis is a statistical technique that is very useful for these types of problems. For example, in chemical process, suppose that the yield of the product is related to the process operating temperature. Regression analysis can be used to build a model to predict a yield at a given temperature. So in this topic, we will going to formulate an equation that will going to predict the possible yield to two variables that has a relationship. So simple linear regression. The simple linear regression considers a single regressor or predictor X and a dependent or response variable Y. So the expected value of Y at each level of X is a random variable. So we can see in the equation that the expected value of Y, given that the X or the predictor is equals to B beta sub 0 plus beta sub 1 time multiplied by x or our regressor. We assume that each observation of y can be described by the model y is equals to b beta sub 0 plus beta sub 1 times x plus e. So, least square estimates. The least square estimates of the intercept and slope in the simple linear regression model are beta hat sub 0 is equals to y bar minus beta hat sub 1 multiplied by x bar. So beta hat sub 1 is equals to the summation of x and y minus the summation of y multiplied by the summation of x divided by n, or our number of samples, divided by the summation of x squared minus the summation of x divided by n, where our y bar is equals to 1 divided by n multiplied by the summation of y, and x bar is equals to 1 divided by n, or our number of samples multiplied by the summation of x. So the fitted or estimated regression line therefore is equals to y hat is equals to b beta hat sub 0 plus beta hat sub 1 multiplied by x. Note that each pair of observations satisfies the relationship. So the equation is equals to y sub I is equals to beta hat sub 0 plus beta hat sub 1 multiplied by x sub I plus e sub I. So note that I is equals to 1, 2, and so on, where e sub I is equals to y sub I minus y hat sub I is called the residual. So e raised to I here is called the residual. The residual describes the error in the fit of the model in the ith observation of I. So we have here the notation S sub x double x is equals to summation of the quantity x sub I minus x bar squared is equals to summation of x is minus the summation of x squared divided by n, and s sub xy is equals to the summation of I times the quantity of xi minus x bar squared is equals to summation of xy minus the summation of x multiplied by the summation of y divided by n. So we will fit the simple linear regression to the oxygen purity in the data in the table 11.1. The following quantities may be computed. So we have the number of samples. We have n is equals to 20. So our summation of x is equals to 23.92, and our x bar or our mean in the x samples is equals to 1.1960, and the summation of y is equals to 1843.21, and the mean for ry is equals to 92.1605, and then our summation of y squared is equals to 170,044.5321, and our summation of x squared is equals to 29.2892, and our summation for x times y, or the summation of xy, is equals to 2,214.6566. And we're going to substitute this we're going to substitute these givens that we have yield to the equation we have discussed earlier, sa the equation s sub x is equals to summation of x squared minus the summation of x to the power of 2 divided by Rn. So we have 29.2892 minus 23.92 squared divided by 20. So we have 0.68088, and in the formula for x sub xy, and for the formula s sub xy, we we also substitute values the values that we have. So the summation of xy is equals to 2,214.6566 subs minus minus the summation of x, which is the 23.92, multiplied by the summation of y, that is equals to 1,843. So to get the value of s sub x double x is equals to summation of x squared minus the summation of x raised to 2 divided by Rn. So we substitute the formula. So we have 29.2892, which is our value of the value of our summation of x squared, minus the summation of x squared. We have 23.92 squared divided by Rn, which is we have 20 samples. So we yield 0.68088, and to get the value of s subscript of xy, we have the summation of xy minus the summation of x multiplied by the summation of y divided by Rn. So we have the value of 2,219.6566 minus 23.92 multiplied by 1,843.21 divided by Rn. We have 10.17744. So we also have to so we can skip this process using our calculator. So we're going to show you how to get these values using our calculator. So first, we already input our values, our corresponding values of x and y in our calculator. So we're going to do now, we will press shift and then 1, and then 3, which is the sum. And we're going to input first. We're going to solve the value of s subscript double x. So the formula has the summation of x squared. So we're going to input x squared, which is 1, minus the summation of x, summation of x, which is 2, and then squared divided by 20, our number of samples. So we get the same answer, 0.68088. And the next, the s subscript xy, we have the formula of summation of xy. So repeat again, shift, and then 1. Then we're going to choose sum, and 5, which is the summation of xy. So minus, repeat again, we're going to press 3 again, sum, and then summation of x, which is 2, and then summation of y divided by 20. So the same answer again, 10.17744. And that is how to come up with that answer using our calculator. So therefore, the least square estimates of the slope intercept are b sub 1 is equals to s subscript xy over s subscript double x is equals to 10.17744 divided by 0.68088 is equals to 14.94748. So and b b sub 0 is equals to y bar minus b sub 1 x bar is equals to 92.1605 minus 14.94748 multiplied by 1.196, we get 90, we get 74.28331. The fitted simple linear regression model with the coefficients reported to 3 decimal places. So we have a regression model. We come up y hat is equals to 74.283 plus 14.947x. So estimating the variance. The error sum of squares is denoted as SS subscript E is equals to the summation of E squared is equals to the summation of the quantity Y sub I minus Y hat sub I squared. It can be shown also that the expected value of error sum of squares is E quantity S sub E is equals to n minus 2 multiplied by our variance. Estimating the variance. An unbiased estimator of variance is equals to variance is equals to SS subscript E divided by n minus 2, where or SA sub E can be easily computed using the formula SA sub E is equals to SA subscript T minus B sub 1 multiplied by S xy. So slope properties. The expected value of B sub 1 is equals to B sub 1, the variance of beta hat sub 1 is equals to variance divided by S xx. Intercept properties. Expected value of beta hat sub 0 is equals to beta sub 0, and variance of beta hat sub 0 is equals to the variance multiplied by the quantity of 1 divided by n plus x bar squared, or our mean of our x divided by s xx. The test statistic could also be written as t sub 0 is equals to beta hat sub 1 minus beta hat sub 1 comma 0 divided by se beta hat sub 1. We would reject the null hypothesis is our absolute value of t sub 0 is greater than our t alpha over 2 n minus 2. Suppose we wish to test our null hypothesis beta is equals to beta sub 0, and our alternative hypothesis is equals to beta sub 0 would be not equal to beta sub 0 comma 0. An appropriate test statistics would be t sub 0 will be t sub 0 is equals to beta sub 0 minus beta sub 0 divided by se beta hat sub 0. We would reject our null hypothesis if our absolute value of t sub 0 is greater than our t sub alpha over 2 n minus 2. And that would be all for my report, and the following topic will be discussed by Miss Nugit.
Okay na.
So, good day, Miss June and Margaret, and today I will be discussing the four subtopics in simple linear regression and coloration. And the first subtopic that I will be reporting is using the t-test. So, the use of t-test is to compare the means of two groups. It is often used in hypothesis testing to determine whether ang process or ang iyang treatment actually has an effect on the population of interest, or whatever two groups are different from one another. So as you can see in the screen, suppose we wish to test the x sub 0, which b beta sub 1 is equals to b beta sub 1 and 2 and 0. Then h sub 1, which beta sub 1 are not equal to beta sub 1 and 0. An appropriate test of this statistic would be t sub 0 is equals to beta hat sub 1 minus beta sub 1 and 0 over square root of sigma hat squared over s sub xx. So the test statistic could also be written as t sub 0 equals to b hat sub 1 minus b hat sub 1, and 0 over standard error b beta beta hat sub 1. We will reject the null hypothesis if ang t sub 0 is greater than t alpha over 2 and n minus 2. Suppose we wish to test h, h sub 0, which beta sub 0 is equals to beta sub 0 and 0. H sub 1, which beta sub 0 are not equal to beta sub 0 and 0. An appropriate statistic would be t sub 0 equals to beta sub 0, beta hat sub 0 minus beta sub 0 and 0 over square root of sigma hat squared 1 over n plus x bar squared over s sub xx equals to beta hat sub 0 minus beta hat sub 0 0 over standard error beta hat sub 0. So we would reject the null hypothesis if ang t over t sub 0 are greater than t alpha over 2 and n minus 2. An important special case of the hypothesis of equation 11 to 18 is h sub 0, which beta sub 1 is equals to 0. Then h sub 1, which beta sub 1 are not equal to 0. So this hypothesis relate to the significance of regression. Failures to reject h sub 0 is equivalent to concluding that there is no linear relationship between x and y. So here in the example, we will test for significance of regression using the model for the oxygen purity data from example 1 to 11 to 1. The hypotheses are h sub 0, which beta sub 1 is equals to 0, h sub 1, which beta sub 2, 1, are not equal to 0. So, nana siya given ng hatag. So, ang beta hat sub 1 is 14.947, then n is 20, s sub xx is equals to 0.68088, and sigma hat sub 2 is equals to 1.18. So this is the formula na ato i-use katong ako gikuan ganina. Then kini siya, the test statistic could also be written as this. So kini, so muna to siya i-apply na ang iyang given, then to calculate the answer man na siya 11.35. The next is analysis of variance approach to test significance of regression. So analysis of variance approach to test significance of regression, which this approach used the variance of the observed data to determine its its regression model can be applied to the observed data. So as you can see in the screen, the analysis of variance identity is this. Then symbolically, SS sub T is equals to SS sub R plus SS sub E. So if the null hypothesis H sub 0, which beta sub 1 is equals to 0 is true, then the statistic will be this. So F sub 0 is equals to SS sub R over 1 over SS sub E over n minus 2 equals ms sub R over ms sub E. Shows the F sub 1 n minus 2. and n minus 2 distribution, and we would reject if f sub 0 is greater than f sub alpha 1 and n minus 2. Then the quantities ms sub r and ms sub e are metric squares. Analysis of variance table. So, mo ni siya. Ang source of variation, sum of squares, degrees of freedom, mean squares, and the f sub 0. Yeah. So, one example. So, we will use the analysis of variation approach this first significance of regression using the oxygen purity data model from example 1 to, 11 to 1. So, ang iyang given kay, so, ang iyang given kay SS tab T, which is equals to 173.38. Then, ang iyang B hat sub 1 is 14.947. So, muna siya. So, the regression sum of squares is kini. Ano ito gamitan yung formula. Then, i-apply itong given, then mana ng answer. 152.13. Then, sa error sum of squares, since error sum of squares may ang gipangita, so, kani nga formula to gamiton, then apply the, ano, apply the given. So, ang answer is 21.25. The next is confidence interval. So, confidence interval, which means the probability that a population parameter will fall between a set of value from a certain proportion of times. So, some statisticians use this to measure ascendingly in a sample variable. And under sa confidence interval kay ang confidence intervals on slope and intercept. So, ang definition is under the assumption that the observation are normally and independently distributed, a 100% confidence interval on the slope beta sub 1 in simple linear regression is kaning formula na yung nakita sa screen. Similarly, 100% a confidence interval on this intercept beta sub 0 is, kasi again, sa screen. Next is, so, this is example sa confidence interval on the slope. So, we will find a 95% confidence interval on the slope of the regression line using the data in example 11 to 1. So the given is beta hat sub 1 is equals to 14.947. S sub xs is equals to 0.68088. Then sigma hat squared is equals to 1.18. So mo ni siya. Na formula ato gamiton. Ang B hat sub 1 minus T sub 0.025 and 18 squared sigma hat 2 over S sub xx less than or equal to beta sub 1 less than or equal to beta's hat sub 1 plus sub 0.025 and 18, and then square root of sigma hat squared over S sub xx. So, muna na siya. Gamitin na ang formula. Muna na siya. Ang given. I-apply ang given. Then, this simplifies to 12.181 less than or equal to beta sub 1 less than or equal to 17.713. So that's all for my report. Thank you. Kaya. So, good day everyone. I am Project Alonso, one of the reporters in Group 9. So, I will continue the discussion about confidence intervals. So, confidence interval on the mean response is where mean hat sub y x sub 0 is equal to beta hat sub 0 plus beta hat sub 1 multiplied by x sub 0. So a 100 multiplied by the 1 minus alpha percent of confidence interval is about the mean response at the value of x equal to x sub 0. So let's say mean sub y is given by mean hat sub y x sub 0 minus t sub alpha over 2, where n is subtracted by 2, square root of sigma squared multiplied by 1 over the value of n plus the subtraction of x sub 0 and the mean of the x values of the x variable raised to the power of 2 over s sub xx, where mean hat sub y x sub 0 can be equal or greater than itself but can also be less than or equal to mean hat by y sub y absolute x sub 0 multiplied by 11 plus 3, 13 minus t sub alpha over 2, where the value of n is subtracted by 2 multiplied by the square root of sigma squared multiplied by 1 over the value of n plus x sub 0 minus the mean of the x value of the x variable to the power of 2 over s sub xx. It can be stated that mean hat sub y x sub 0 is equal to the addition of beta sub 0 and beta sub 1 times x sub 0, where it is computed from the fitted regression model. We'll go next. So, example 11 to 5, oxygen purity confidence interval on the mean response. We will construct a 95% confidence interval about the mean response for the data in example 11 to 1. The fitted model is mean sub y x sub 0 is equal to 74.283 plus 14.947 x sub 0, and the 95% confidence interval on Earth is found from equation 11 to 13. As mean hat sub y x sub 0 added or subtracted by 2.101 multiplied by the square root of 1.18 times 1 over 20 plus x sub 0 minus 1.1960 raised to the power of 2 over 0.68088. So, suppose that we are interested in predicting mean oxygen purity when x sub 0 is equals 100%. Then our mean sub y x sub 1 is equal to the addition of the given, which is 74.283 and 14.947 times 1. It is equal to 89.23. And since there are 95% confidence interval, then 89.23 added or subtracted to 2.101 is multiplied by square root of 1.18, then multiplied by 1 over 20 plus the subtraction of 1 and 1.1960 raised to the power of 2 over 0.68088. So therefore, the 95% confidence interval on mean sub y with an absolute given of 1 is greater than or equal to 88.48 but less than or equal to 89.98. So this is a reasonable narrow confidence interval. We'll go next. So let's move on to the prediction of new observations. So these are the prediction interval. 100 multiplied by 1 minus alpha percent of prediction interval on a future observation y sub 0, and the value of x sub 0 is given by y sub 0 minus t sub alpha over 2, where n is subtracted by 2, then multiplied by the square root of sigma squared multiplied by 1 over the value of n plus x sub 0 minus the mean of the x values of the x variable raised to the power of 2 over s sub x. So where y sub 0 is equal or less than to the given formula, which refers to figure 11 to 14. And using the formula that you can see below, which is similar sa formula ganiha, pero the difference is that na-change na siya as y sub 0. So you can use that formula to find the value of y sub 0. So next. So example 11 to 6, oxygen purity prediction interval. So continuation. So to illustrate the construction of a prediction interval, suppose that we use the data in example 11 to 1 and find a 95% prediction interval on the next observation of oxygen purity x sub 0 is equal to 1%. And with the use of the equation 11 to 14 and recalling from example 11 to 5, we can find that y sub 0 is equal to 89.23. And using the given formula, we can replace y sub 0 with the given value, which is 89.23, before applying it to the formula. And as you can see, the prediction level of interval simplifies that 86.83 is less than or equal to y sub 0, which is also less than or equal to 91.63. Therefore, this is a reasonably narrow prediction interval. We'll go next. So there are things that needs to be considered, and some of that are fitting a regression model requires several assumptions. So first is errors are uncorrelated random variables with mean zero. Second is errors have constant variance, and third is that errors are normally distributed. So the analyst should always consider the validity of these assumptions to be thoughtful and conduct analysis to examine the adequacy of the model. So let's move on to residual analysis. So the residuals from a regression model are E sub I is equal to the subtraction of Y sub I and Y hat sub I, where Y sub I is an actual observation and Y hat sub I is the corresponding fitted value from the regression model. So it is frequently helpful to analyze the residuals in order to verify the accuracy of the assumption that the errors are roughly normally distributed with constant variance and to decide whether or not to include more terms in the model. We'll go next. So the regression model for the oxygen purity data in 11 to 1 is y hat is equal to the addition of 74.283 and 14.947x. We'll go next. As you can see in the table, there is an indicated value in each column of hydrocarbon level, or the X. It includes the oxygen purity, predicted value, and the residual, which is the subtraction of Y and Y hat. So the observed and predicted values of Y at each value of X from this dataset, as well as the related residual, are shown in table 11 to 4. These values, which were determined using Minitab, exhibit the standard number of decimal places for computer output. Next slide, please. So as you can see in the figure, it is an example of a normal probability plot for the residuals. Since the residuals fall approximately along a straight line in the figure, we conclude that there is no severe departure from normality. So since the graph clearly shows a straight line, then wala kayo siya changes, then it is considered as normal probability. Well, I could next. In this given figure, we can see that the residuals are also plotted against the predicted value and against the hydrocarbon levels X sub I in figure 11 to 12. So therefore, these plots do not indicate any serious model inadequacies. So that's all for my report. The next reporter will continue the discussion of the remaining topics. Thank you.
So good day everyone, I'm Jadrustin Albals. So I'm going to continue the discussion of the coefficient of determination or R squared. So the coefficient of determination is a number between 0 and 1 that measures how well a statistical model predicts an outcome. So we have here the formula of the coefficient of determination R squared. So R squared is equals to sum of squared residuals over the sum of squared of totals equals to 1 minus sum of square of errors over sum of squares of totals. So that's called the coefficient of determination and is often used to judge the adequacy of a regression model. And then we often refer loosely to R squared as the amount of variability in the data explained or accounted for by the regression model. Pareho ko next, no? So these are the example of the coefficient of determination. For the oxygen purity regression model, we have R squared. So we're going to substitute the value of the sum of squared residuals over the sum of square of total. Then we have 152.13 over 173.38 is equals to 0.877. Thus, the model accounts for 87.7% of the variability in the data. Wala ko next month. So, the correlation coefficient is a numerical measure of the strength of association between the independent variable x and the dependent variable y. So coef- the correlation coefficient is defined as rho equals to sigma xy over sigma x times sigma y, where p is the correlation coefficient and then the sigma xy as the covariance between y and x, then the sigma x and sigma y as the population standard deviations. Then the conditional distribution of y for a given value of x is equals to x as f y absolute x, then times the quantity of y is equals to 1 over square root 2 pi sigma y absolute x times exponential minus 1 half times 1 y minus b sub 0 minus b sub 1 over sigma y absolute x squared minus 16, where where beta sub 0 is equals to mean y minus mean x rho sigma y over sigma x, then the beta 1 is equals to sigma y over sigma x times the rho, or the correlation coefficient. Kaya ko next notes. So this formula, as what you can see in the screen, is the estimation of rho, or the correlation coefficient, or we can also write this one as r squared equals to beta hat 1 squared, then the s sub xx over s sub yy is equals to beta hat 1 times x sxy over sst is equals to sum of squares residual over sum of square total. Wala kog next nog. So it is often useful to test the hypothesis where null hypothesis, the population correlation coefficient is not significantly different from zero, so there is not a significant linear relationship correlation between x sub 1 and x sub 2 in the population. Then the alternate hypothesis, where the population correlation coefficient is significantly different from zero, there is a significant linear relationship correlation between x sub 1 and x sub 2 in the population. And then the appropriate statistic for this hypothesis is the p-value is equals to r square root of n minus 2, where n is the sample size and then the r is the sample correlation coefficient over square root of 1 minus r squared. And then we're going to end then if the calculated value is in the tail, then cannot accept the null hypothesis that there is no linear relationship between these two independent random variables. But if the calculated p-value is not in the tail, then cannot reject the null hypothesis that there is no linear relationship between the two variables. Ayaw kog next no. So the test procedure for the hypothesis is if the p-value is less than the significance level, so we can reject the null hypothesis because there is sufficient evidence to conclude that there is a significant linear relationship between x and y because the correlation coefficient is significantly different from zero. Then where p-value is somewhat more complicated in this case, then the appropriate test statistic is the z0 is equals to hyperbolic of inverse arctangent r is equals to hyperbolic arctangent p0 times n minus 3 or to the power of 1/2. Then we can reject the null hypothesis. Let's go next. Then the approximate 100 or times 1 minus alpha percent confidence interval is the hyperbolic of tangent times the quantity of hyperbolic arctangent r minus z alpha 2 over square root of n minus 3 is equals to rho hyperbolic tangent, then the quantity of hyperbolic arctangent r plus z alpha 2 over n minus 3. So that is the that's the a significant linear relationship. Wait a no. Relationship between x and y because the correlation coefficient is not significantly different from zero. Palihog ko next na. Then example of correlation wire band pole strength in chapter 1 section 1 to 3 and application of regression analysis is described in which an engineer at a semiconductor assembly plant is investigating the relationship between pulse strength of a wire band and two factors were length and die height. In this example, we will consider only one of the factors, the wire length. A random sample of 25 units is selected and tested, and the wire band pull strength and wire length arc observed for each unit. The data are shown in the table 1 and 2. We assume that pull strength and wire length are jointly normally distributed. In figure 11 to 13 shows a scatter diagram of wire bond strength versus wire length. We have used the Minitab option of displaying box plots of each individual variable on the scatter diagram, and there is evidence of a linear relationship between the two variables. So as you can see, the figure 1113, which is a scatter plot of wire bond strength versus wire length, the all points here is close to the line if we make a line at the center, so the absolute value of our correlation coefficient is high. I'll go next. So we have our Minitab output for example 11 to 8, the regression analysis, strength versus length. Then the regression equation is strength equals 5.11 plus 2.90 length. Then the predictor of coefficient, we have the constant 5.115, 1.146, 4.46, 0.00, and then the length, you have 2.9027, 0.1170, 24.80, and 0.0. So we have our sum total is equals to 3.093, and the required squared equals to 96.4%, and then the adjacent is equals to 96.2%. And then we have the analysis of variance. Regression 1.588.5.9, and then the MS 5885.9 and 615.08 and 0.00, and then the residual error 23, 220.1 and 9.6. So we have the total of 6105.9. Next. So this is the continuation. Now our SXX is equals to 698.56, and the S sub XY is equals to 2227.7132, and the sample correlation coefficient is the R equals to S sub XY over S sub XX and times SS sub t, where SXY is equals to sample covariance, and then the S sub XS is equals sum of squared deviations from the mean value of X, and then we have sum of squares of total. Then we're going to distribute it. Then our value of XXY is equals to 2227.7132 over the SXX is the 698.560 times 6105.9 power of 1 half, so we have 0.9812. Note that R squared is equals to 0.9818 squared, so we have now 0.9640, which is reported in the Minitab output, or that approximately 96.40% of the variability in pulse strength is explained by the linear relationship to wire length. I hope next. So now suppose that we wish to test the hypothesis with alpha equals 0.05 we can now compute the t-statistic of equation 11 to 21 as the t-value is equals to r square root of n minus 2, where the r is the sample size, n over 1 minus r squared. Then we're going to contribute it again. Our r square root of n minus 2 is 0.9818. Square root of 23 over 1 minus 0.9640 is equals to 24.8. So this statistic is also reported in the Minitab output as a test of null hypothesis beta 1 is equals to 0, because t-value because our t-value is equal to 0.025.23 is equals to 2.069. So now we reject null hypothesis and conclude that the correlation coefficient is significantly different from 0. So finally, we may construct an approximate 95% confidence interval on R from equation 1123, since we have inverse of hyperbolic arctangent 0.9818 is equals to 2.3452. Equation 11 to 23 becomes hyperbolic tangent over times the quantity of 2.3452 minus 1.96 over square root of 22 equal to is rho equals to hyperbolic tangent times the quantity of 2.3452 plus 1.96 over square root of the 22. So which reduces to 2. We have now rho equal to 0.9585 and 0.9921. There will next now. So transformation and logistic regression. We occasionally find that the straight line regression model y is equals to b sub 0 plus beta 0 plus beta 1 x plus e inappropriate because the true regression function is nonlinear. Sometimes nonlinearity is visually determined from the scatter diagram, and sometimes because of prior experience or underlying theory. We know in advance that the model is nonlinear. Occasionally, a scatter diagram will exhibit an apparent nonlinear relationship between y and x. In some of these situations, a nonlinear function can be expressed as a straight line by using a suitable transformation. Such nonlinear models are called intrinsically linear. Next. So here is example 11 to 9 windmill power. A research engineer is investigating the use of a windmill to generate electricity and has collected data on the DC output from this windmill and the corresponding wind velocity. The data are plotted in figure 1114 and then listed in table 11 to 5. So we can see the observation number and then the observation number, which I, then wind velocity mph, x sub 1, DC output y, then I'll go next notes. So in figure 11 to 14, plot of DC output y versus wind velocity x for the windmill data. Yung nasa left, muna siya ang kanang plot of DC output sa y and then sa wind velocity, and then kaning sa right Muna siya ang kanang kuan, plot of residuals A versus fitted values Y for the windmill data. Pareho ko next node. And this one, the plotted diagram is a plot of DC output versus X prime equals to 1 over X for the windmill data. Pareho ko next node. Then, as you can see, the figure 11 to 17 plot of residuals versus fitted values y hat for the transformed model for the windmill data, and then the figure 11 to 18 normal probability plot of the residuals for the transformed model for the windmill data. A plot of the residuals from the transformed model versus is shown in figure 11 to 17. So this plot does not reveal any serious problem with inequality of variance. The normal probability plot shown in figure 11 to 18 gives a mild indication that the errors come from a distribution with heavier tails than the normal. Notice the slight upward and then downward curve at the extremes. This normal probability plot has the z-score value plotted on the horizontal axis. Since there is no strong signal of model inadequacy, we conclude that the transform model is satisfactory. So that's all about our report, and thank you.